Hi, welcome to Chapter 14, Chemical Kinetics Overview, Part 4, where we're going to go over Section 14.5 in the book, which is temperature and rate. So before we get into the new stuff, let's review a little bit about the integrated rate law. What is the integrated rate law used for? Well, it's used to determine the amount of reactant or product present after a certain amount of time. Or you could use it to estimate the time required for a reaction to proceed to a certain extent. When given data of concentration versus time, what two graphs must be made in order to determine whether the order of the reaction is first or second? So the two graphs that you want to make are a graph of the natural log of the concentration of A versus time, and a graph of the 1 over the concentration of A versus time. Whichever of these graphs gives you a straight line or a linear graph, that is the order. So if it's the natural log of A versus time, then it is first order. If it's 1 over the concentration of A versus time, then it is second order. How is the slope of the lines related to the rate law? Well, that's how we get our K, which is our rate constant. Okay, if it is first order, this is the graph you're going to have for first order. And you see here the slope is equal to negative K. So you get the slope and then you take the negative of that and that'll give you K. If it is second order, you see here the slope is equal to K. So you take the slope of this line and that'll give you K, which is the reaction rate constant. How can you check without actually making the graph? Because it's very time consuming to make the graph. Well, you could actually calculate the slope between a couple data points and see if it's changing. If the slope is constant, then that is the order. All right, so if you're taking the natural log of A versus time and you take the slope between a couple of these points and you get a constant slope, then it is first order. If you take 1 over the concentration of A versus time and take the slope between those, then it is second order. Whichever one gives you a constant slope, that is the correct order. What about the half-lives? How is the half-life affected by concentration in a first order reaction? Well, if it's a first order reaction, the half-life is not affected by concentration. The half-life is constant. So if we look here, this is for first order. This is for 0 order, and this is for second order. You see here, the time, this here is our time. So each of these times is constant. It is not changing with concentration. Because remember, the concentration of A is changing as we go down here, but the time is staying the same. So that means it is first order. If it is second order, though, what is happening to our time, our half-life time here? Let's look at it. What do you notice is happening with these lines? The time that it takes for half of the concentration to be used up is increasing. So the half-life increases as your concentration decreases. This is for second order. And why is that? Well, look at the equation. The half-life time is 1 over K times the concentration. So as this concentration decreases, the time is going to increase. So how can this be used to determine the order of a reaction? Well, you look at the graph, okay? And then you look at the amount of time it's taking. So you say, here I started at 0.2, half of that would be 0.1. And this is the amount of time it takes. Half of 0.1 would be 0.05. And you look at the time difference between, and you see it's the same. If it's the same, it's a first order reaction. If the time is increasing, then it is a second order. What is the order if the time decreases? Well, if the time decreases, then it is 0 order, and that's what we're showing here. See, notice the time is getting smaller here as our concentration is decreasing. So let's talk about some factors that affect the reaction rate. Temperature, the amount of collisions you have, the orientation of your molecules, and a specific amount of energy that you need for the reaction to take place, and that is called your activation energy. So how does temperature affect rate? Well, generally, as the temperature increases, the rate increases. So as temperature increases, your rate is going to increase. The rate constant is temperature dependent. Remember, in our rate law, we had some constant times concentration of A or B or whatever. But this here, K, is your rate constant, in case you forgot. And the rate constant is temperature dependent. As you can see here we have K versus temperature. And how does it actually, as the temperature increases, your K increases. So K increases as the temperature increases. Your rate constant actually doubles approximately, in this case over here, with every 10 degrees rise. So it has a significant effect. The frequency of collisions is also important, okay? In order for a reaction to occur, the molecules have to collide. So the collision model is based on the kinetic molecular theory. Remember the kinetic molecular theory, you had molecules or atoms, and they were moving around, and they could collide with one another. They move in a straight line until they bump into something else. So molecules must collide to react. They must hit each other to actually react. If you have more collisions, you have more reactions, okay? It's a probability. If you bump into something once, or if you bump into something 10 times, the 10 times one, you're going to have a greater chance of reacting. So if you have more molecules, the reaction rate is faster. And what do we mean by more molecules? If your concentration is increased, you will have more molecules and your reaction rate will be faster. When we have these chemical reactions, what's actually happening? Bonds are being broken and new bonds are formed. And this can only occur, these molecules can only react if they collide with each other. So, orientation of the molecules. So the molecules can often collide without actually forming any products. They have to collide and hit each other in just the perfect alignment. So alignment of the molecules properly can lead to a chemical reaction. When the alignment is proper, then bonds must be broken and made, and the atoms need to be in the proper position for this to happen. Furthermore, molecules must collide with the correct orientation and with enough energy to break bonds and then actually reform bonds. So if you look at this diagram down here, before the collision, you have this one chlorine bumping into this. And in this case, you see the two chlorines are bumping into each other. And they actually bond. So this bond here will break, and this bond will form. And this will be a successful reaction. What happens if this chlorine does not hit the chlorine? It hits the other side of the molecule. Well, then this is not the proper alignment, and no reaction will occur. So if you can increase the amount of collisions, the probability of you having a proper alignment increases. So your reaction rate will increase. Not only do they have to be aligned properly, they have to have enough energy to react. And that amount of energy that they need is called your activation energy. So your activation energy is the minimum energy needed for a reaction to take place. And we call it EA. E for energy, A for activation. So it's kind of like if you've ever played golf or mini golf. This golfer has to get the golf ball above this hill so that it could actually go into the hole. If he doesn't hit it hard enough, it will roll back down. And the height of this hill is your activation energy. So you have to have enough energy to kind of get over this so that the reaction can occur. So think of it as an energy barrier. You must overcome it for the reaction to take place. So the transition state or activated complex. Reactants gain energy as the reaction proceeds until a particle reaches a maximum energy state. Okay, when you are at this maximum energy state, you are an activated complex. The organization of the atoms at this high energy state is called the transition state because you are ready to react, or it's called the activated complex. The amount of energy you need in order to have the molecule at this state is called your activation energy. So let's look at what's happening here. Here is our activation energy plot. You see we have potential energy on the y-axis, and we have the reaction progress on the x-axis. So plots are made to show the energy process by the particles as the reaction proceeds. At the highest energy state, a transition state is formed. Here is our highest energy state. Here is our activated complex, okay? And this is our transition state. The molecule up here has enough energy for the reaction to proceed. Okay, in this particular case, here are my reactants, and here are my products. Since my products are at a lower energy than my reactants, this reaction here is exothermic. Again, because my products end at a lower energy than my reactants, this reaction is exothermic. An endothermic reaction would look like this, where your products end at a higher energy than your reactants. Your rate constant depends on the magnitude of your activation energy, which is right here. This is your EA, this height here. The amount of energy that is released, in this case, because it's exothermic, is your delta E. In this case, your delta E is not released, but it is absorbed. Remember, endothermic absorbs energy, exothermic releases energy. So here is the same plot, but we're zooming in on the molecule. What is happening? Here we have our molecule, and we are increasing its energy. And we increase its energy until it gets to this point up here. When it gets to this point up here, what's happening? The bond between the carbon and the nitrogen breaks. Then this thing kind of flips over, and then the carbon and carbon form. So in order to get this bond to break, you have to heat it up to, or increase its energy until you get to this activated state. It breaks that bond, allows this half the molecule to kind of flip around and rebond at a lower energy. So again, this diagram was the one on the previous slide. It shows the energy of the reactants, which is right here, and the products. And here is your delta E, which is your change in energy of this reaction. And the high point here is called your transition state. The species present at the transition state is your activated complex. It is ready to react. It has enough energy. The energy gap between the reactants, so this right here is your activation energy barrier. That is the mountain you have to overcome for the reaction to occur. Now, if you remember way back when we were doing gas laws, we said that not all of the molecules are moving at the same kinetic energy. They have a Maxwell-Boltzmann's distribution of that. And that's what's being shown here. Here is your distribution of your energies. Okay, so temperature is defined as a measure of the average kinetic energy of a molecule in the sample. So here we have low temperature. Notice the curve is higher and skinnier. Here we have high temperature. As we raise the temperature, the peak of this kind of goes down, but it gets broader. Okay? At any temperature, there is a wide distribution of kinetic energies. As the temperature increases, the curve flattens and broadens. So flattens, comes down, and broadens. Gases have an average temperature, but an individual molecule has its own energy. So overall, the gas will have an average kinetic energy. But if we're just looking at individual particles, some of them are higher energy than others. At the high energy, the more molecules at higher energies or higher temperatures, then you have more molecules that will possess the energy needed for the reaction to occur. What am I talking about? Look at the red graph here. Here is the minimum energy you need. Here's your activation energy right here. The red one has a larger area here, so it has more molecules that can react. So thus, at higher temperatures, you have a larger population of molecules that have a higher energy. So what's the result of this? You're going to have a faster reaction rate. And remember, this dotted line represents the activation energy. So as the temperature increases, so does the fraction of molecules that can overcome this barrier. As a result, your reaction rate increases. So that is why as you heat things up, reactions tend to go faster. So if you remember the Maxwell-Boltzmann's distribution, it's this range of kinetic energies. Okay, and if we want to know the fraction of molecules, which is F, can be found through an expression like this. So E to the negative, remember EA is your activation energy. And it has to be in joules. And R is your gas constant. And you have to use 8.314 joules per mole Kelvin. And T is temperature, and this is important, has to be in Kelvin. So if you remember, Kelvin is equal to your degrees Celsius plus 273. So Arrhenius developed a mathematical relationship between K. Remember, K is our rate constant. Remember, rate equals K times the concentration of some reactant. Okay? And EA is our activation energy. So here is the relationship he came up with. Okay, so we define EA as our activation energy, R is our gas constant, T is temperature in Kelvin. But what is this A right here? This A is a frequency factor. So it kind of represents the likelihood that collisions would occur with the proper orientation for the reaction. But you see why K is dependent on temperature? T is right here. So the relationship between activation energy and temperature. So Arrhenius noted the relationship as such. And this is all nice, but it would be nice if we could rearrange this and write it in a form y equals mx plus b. So we take the natural log of both sides. And then we just rearrange it so that it's like y equals mx plus b. So we have the natural log of k is equal to negative EA over RT plus the natural log of A. So then if we plot the natural log of k versus 1 over t, the slope is negative EA over R. So therefore, we could determine experimentally, we could, if K is determined experimentally at different temperatures, and we plot it versus 1 over temperature, we can figure out the activation energy. And what's nice is if we know 2 different Ks at 2 different temperatures, or say we know 1K, the activation energy, but 2 different temperatures, we can calculate what the rate constant K2 is at a separate temperature. So we could use this equation to compare Ks at different temperatures. So let's summarize what we learned in this section. What factors affect K, which is the rate constant? Mainly we talked about temperature today. Temperature affects K. And how does it affect it? As the temperature increases, K increases. Because remember, K is equal to E to the minus EA over RT. Okay? We didn't talk about this in this section, but we will in the next video lecture. The presence of a catalyst will also affect your rate constant. What is activation energy? That is the minimum energy you need for a reaction to take place. We call that EA. What data would you need to determine the activation energy experimentally? Well, you have to measure the rate constant at various temperatures. So you need the rate constant K at various temperatures. Then you would make a plot of the natural log of K over 1 over T. And the slope of that is equal to negative EA over R, and then you could solve for EA. Remember, temperature must be in Kelvin, and R must be 8.314 joules per mole Kelvin. And that is the end of our video.